So, hi everyone, welcome to this IEA Wind Task 43 webinar series on the topic of why does the wind energy sector need to start talking about digital twin architecture. My name is Sarah Barber. I lead the Wind Energy Innovation Division at the Eastern Switzerland University of Applied Sciences. I also co-lead the IEA Wind Task 43, which I'll tell you about in a second. So I'll get straight into the presentation. I'd just like to ask all of you to make sure your microphones are turned off. It's got a bit of background noise. If you've got any questions while we go along, please feel free to write in the chat, and we'll try to respond at the end. We've got quite a few speakers, so we kind of need to push on with them. The plan is to have about 15 minutes at the end for discussion. Before I start talking about the content, I just want to present my slide on fostering an open and inclusive culture at the meeting today. So this has been developed with the European Academy of Wind Energy's Diversity Committee, and we just like to remind or suggest that we all try to use gender-sensitive language when we're talking to make everyone feel included. We try to use non-violent communication for constructive conversations. So that means speaking from our own observations, and then also practicing active listening in order to empower people to find solutions themselves. If you want to know more about that or talk about it, please feel free to contact me afterwards. So the agenda today is that I'm going to do in the next 2 minutes, a quick introduction. And then we've got 4 speakers. So Carlos Rodriguez from Suzlon, Amy Robertson from NREL, Tom Clark from Octu, Marcus Wiens from Fraunhofer EVIS, who are going to give some examples. So the first 2 are use case examples. The second 2 are examples of architecture being applied to digital twins. And then we're hoping to have a discussion at the end where we've prepared a Mentimeter quiz for you to all give us your inputs in kind of hopefully an efficient way. So yeah, please put any questions in the chat if something's unclear. I'm just going to push on. So just quickly, IEA Wind. IEA is the International Energy Agency, and they've got something called a TCP, which is a technology collaboration program, which is a cooperation of 24 different countries, and they run tasks on loads of different topics, which are shown here on the right, to do with wind energy. So Task 43 is just one of them. It's about digitalization. And we want to unlock the full value of wind energy through digital transformation. And we see ourselves as a digital transformation catalyst who drives open collaboration to deliver insights, recommendations, standards, and tools in these 3 key areas of data, culture, and co-petition. These 3 words actually come from a paper that we wrote a few years ago called The Grand Challenges in the Digitalization of Wind Energy, where we came to the conclusion that data, culture, and co-petition are the main challenges. Co-petition, by the way, isn't a mistake. It's a combination of the word competition and cooperation. And so Task 43 actually looks at these 3 topics in 3 working groups, which are then complemented with some working groups on use cases and dissemination. So some examples of what we do. We've delivered a new data model on wind resource assessment. We're developing a new wind energy domain ontology. We've written a paper about knowledge engineering and wind energy. We've published an ontology portal called Technoportal, and we're working on some different best practices and roadmaps. So getting onto the topic of digital twins. So I guess you're all here because you think digital twins, I'm assuming you think digital twins are important and interesting, and they're kind of being talked about as things that are key for the wind sector because of their ability to provide virtual replicas of physical systems, but also then to enable real-time monitoring and maintenance, increased efficiency, identification of issues, and also better decision-making. But why architecture? So the focus of today is about architecture. So we think that architecture ensures a better integration and interoperability when you want to scale up your digital twins. And we think that it allows for a consistent data collection and analysis. And if we define common architectures across the industry, we think that this should be able to enable different stakeholders to collaborate better and then ultimately driving down the costs. But we're going to get into that now with our speakers. I've got one more slide, which is illustrating something to do with architecture. What is an architecture? So the first stage of an architecture might be just to even define what we mean by the word digital twin. So there's several definitions knocking around. We put them together in this conceptual model, where you can see these different types: physical systems, digital systems, prototypes, instances, but then communication types like model, shadow, twin, functionality types. And so there's quite a lot of discussion about that. And even if we just had a common definition of what we meant by those, I think it would make it easier to talk about digital twins. So now moving on to the first presentation. If you're ready, Carlos, I'll just ask you to start. And then after that, move on to the next presentation.
Yeah. So I'm Carlos Rodriguez. I'm aerodynamics and load specialist at Suzlon, and I'm going to introduce you to an example of a digital twin. First, making a very brief introduction of my company. Suzlon is the #1 wind turbine manufacturer in India. We've installed 20 gigawatts of wind power so far, with 30,000 wind turbines. We're present in 17 countries, but mostly based in India. We're 6,000 employees strong, have around about 2,000 customers, and have had a revenue of roughly $500 million in 2021. Then, well, just the problem we are trying to tackle, and the problem which we actually have, is sometimes we have a wind turbine that is overperforming, that is behaving not behaving as expected. So in the right diagram, you can see the actual power, the power measured, like presented as a power curve, and then what in a continuous line, and then the nominal power, what it should be producing. So then the next slide. So then what we do in order to tackle that problem, that difference between the measurements and what is the expected power curve, is we build up some kind of architecture. We call it a digital twin, that where the consists of the pieces you see in front of you. The inputs would be an aeroelastic model of the turbine you just saw, and real field data from our SCADA system. It's called Trinity, and at the left bottom corner, we feed those inputs into a digital twin. Let's call it a GUI that transforms those inputs into simulations. Then at the right bottom, at the corner right to the bottom, you can see a new power curve, which is the simulated power curve, with the measurements that we have, and using the elastic model that we developed. So then moving on to the next slide. Once we have that, we have the measurement, like what we have, what we would like to have, and a simulation that resembles reality somewhat. Then we can start kind of tweaking with the inputs, and simulate whichever conditions we think are causing the problem. In this case, I'm showing different wind distributions, because we thought the problem would be could possibly be, or probably be, a misreading of the anemometers, of the wind sensors at the turbine. So we combine those different wind distributions with and we feed them into the aforementioned GUI, digital twin, and we finally come up with two new power curves. One, I call it more wind, and the other less wind. More wind to the left and less wind to the right. But yeah, comparing all those power curves that you see, all those 5 power curves, like the actual power, the actual measurement, the nominal power, what the turbine should be doing, simulated power, our first attempt to kind of harness that into a simulation, into something that we can tweak with the computer. And then the more wind and less wind, meaning the likely wind distributions that could be happening at the site. Then we go to the next slide, which should be there. So yeah, the first the power curve that better matches what is expected from the turbine, and assuming that the turbine hasn't got any damage or is relatively new, assuming that you're also that we've also checked the controller parameters, and yeah, let's say that all the other uncertainties are checked and and the only one left is the wind. Yeah, we can come to the conclusion that the most likely explanation for that overpower is that the wind are misrepresented. And we come to this conclusion because we have a reliable, meaning realistic model, our digital twin, and we can feed it with whichever, in this case, wind conditions for the presentation, but exactly the same thing can also be used to try, let's say we have some uncertainties with the polars, like with the aerodynamic design. We can also try different polars. We have seen some uncertainties. Yeah, I'm going into any questions kind of. Yeah, let's say we have some uncertainties with the structural modeling. We can also change different parameters there, feed them into the model, into the digital twin, and see which one reflects better reality or what is expected from the turbine, and so on. We can pretty much, once you have framed your reality into, like, or you have put match your reality into the computer, you can pretty much do anything with it and try whatever you are looking for. And usually you come to a much better, much more informed conclusion, because right now all these, until now, all these discussions are become very philosophical without really real numbers, let's say. And that's it from my side. It's any questions?
All right, thank you. I'll just suggest, so if you've got questions, put them in the chat or save them until the end, and we'll have a Q&A at the end. Okay, so thank you, Carlos, for the insights into Suzlon. So I'll move on to Amy.
Yeah, hi everyone. I'm Amy Robertson. I'm the Offshore Wind Group Manager at the National Renewable Energy Laboratory in Colorado in the United States. And I'm going to be talking today about some of the work that we do with physics-based modeling tools. I think, as Sarah mentioned, I am the task lead of the IEA Wind Task 56 in IEA Wind, and this one's focused on trying to verify and validate the tools we use to design offshore wind systems. And the idea is, can we use those tools now as digital twins? So yeah, the outline of what I'll be talking through is adapting some of these open fast-like modeling tools, so Flex, HAWK2 type modeling tools for digital twin use. An example of how we're using digital twins in an application, and then goals for digital twins and development needs. Slide. So as I was saying, multi-physics tools, we've been focused on these things like FAST, HAWK2, Flex for many years to try to make sure that we can accurately design these offshore wind systems. But there's the idea that now we can use these same modeling tools as digital twins. So again, trying to have a numerical replication of an actual physical asset, and what are the roles that we can then use for that model for actually doing operations and maintenance of the wind system. Next slide. So this is just a overview of what OpenFast looks like. So for those not familiar with some of these engineering level physical modeling tools, these are what we call mid-fidelity tools. They're not high fidelity CFD type tools where you can completely resolve the physics of the offshore wind system, but something that's simplified so that it can be run quickly. So the idea is that if you have numerical models that can run rather quickly, then there's a potential to have them integrated within the wind farm to actually help in making decisions for that wind farm. But even these mid-fidelity tools, they're starting to get quite complex. So there's it's not so easy to run them so quickly anymore. So there's even the potential to look at more simplified models. So yeah, just showing here also that those modeling tools in OpenFast do take in kind of the full representation of the wind, the waves, and the structure itself. So in terms of how do we use those OpenFast-like tools for digital twin implementations, you can just use a model of a wind system within OpenFast directly as a digital twin. Again, you can have that being an exact replication or as close of a replication as possible to a physical asset to help you make decisions. But to be able to do something more quickly, then you might want to look at something more simplified. So you can look at maybe lower fidelity modeling tools, or you can use some of those mid-fidelity capabilities, such as through OpenFast, and use them in a more time-efficient manner. So this slide is showing how we've adopted OpenFast specifically for digital twin implementation by taking that OpenFast model, doing a linearization of it, and then integrating that linearized model with measurements to get a representation of the system that you can use in a real-time way. Next slide. So the application where we've used this specifically is for the Steesdale Tetraspar demonstration project. This is the 3.6 megawatt demonstration project that was done in the last few years. And what we're trying to do is take some small set of measurements from this wind system and use this digital twin as a virtual sensor. So let's say you have the wind speed measurement and I think we just had some SCADA data, which did not include the wind speed measurement. And we tried to take that limited set of information, say, can we understand what's going on throughout the wind system? So as you can see on the lower left there, we are trying to understand, can you predict what the wind speed is, the thrust, the tower base moment, and that tower middle moment based on this very limited set of information that most wind turbines typically have readily available. So can you use your digital twin as what we say a virtual sensor? And you can see in the results on the lower left there that this is showing what the relative error is in those predictions. So in this case, we actually had a fairly well outfitted system with a lot of measurements. So we pretended like we didn't have those so that we could then try to predict them and compare how well we were doing. So you can see that there's some level of error, but actually it was getting the trends quite well, but there's definitely area for improvement. Next slide. So yeah, there's encouraging results in general. We had about a 10 to 15% inaccuracy, I guess, in our results, but right now we've developed the capability so that you can predict certain types of sensors, and we'd like to expand that more to be able to look at things like what is the wave climate, for instance, of the system, as well as additional degrees of freedom, like in the blades and things like that. So we really want to drive towards having this model be able to tell you what is going on throughout the system so that you can, again, then make decisions based on that information. Next slide. So I know Sarah touched on this a little bit, but I was just going to say now, okay, now that you have this representation of the system, what types of things can you do with it? So here we're just showing the type of information you can gain from that digital twin, but the applications that you can then use it for are things like anomaly detection, condition monitoring, predictive maintenance. So this is how assessing what the health of the system is, what is the status of the system, and then make decisions for a predictive maintenance type scenario where you're able to understand kind of how the system is accumulating damage. So you can make proactive decisions on how you want to make maintenance type decisions. Next slide. And another application area is performance optimization. Again, if you have this information coming in and you have a model, you can start understanding how the system is performing, like we saw in that last presentation. But you can make decisions on things like the controls. How are you controlling your wind farm in terms of how much power you're getting out versus maybe how much load accumulation you're seeing. This can be done at the farm level or at individual turbines. And you can actually look at ways through that digital twin to understand how you can improve the performance or lessen the loads maybe within the wind farm itself. Next slide. And then finally, this isn't a direct, I guess, link, but as you have this model and you're seeing what the real world properties are, again, looking back at that last presentation, you can actually think about how you need to improve your models or your physics and your models. And by doing this, you can then understand how your models are being used to design these systems, and maybe think about how you need to improve your models to be able to improve what the actual physical representation of these systems are based on what you're originally predicting what they were. So getting that feedback loop of assessing what your model thinks the system looks like, getting those measurements, and improving your models and design process to get to a better representation in the end. And I think next slide, that was probably it. Yeah, thank you very much.
Perfect. Thank you very much. Again, if you have any questions for Amy, just put them in the chat or hold on until the end. So now I've seen two examples. Obviously, there's hundreds of more examples, but we've just seen two interesting examples, I think, of digital twin applications. And now we're going to move on to the next topic. So we've now got two presenters who are talking about examples of architecting, so not necessarily focusing on the physics or the data or the models, but focusing on how these different components get stuck together and what needs to be thought about for that. So I'll pass on to you, Tom.
Thanks very much, Sarah. So next slide, please. So I'll be sort of taking us through three steps. First of all, kind of a little bit of a cover, a little bit of a follow-on really from how Sarah introduced the topic of digital twins, and expose you to some of my controversial opinions about what they actually are. Then I'm going to talk about actually what I call the accidental data lakehouse. So we did this project called AeroSense, working with Sarah a couple of years ago now to build a digital twin that allowed us to do rotor blade aerodynamic monitoring, and had some interesting experiences essentially sort of storing and managing data. And so I want to pick up on some lessons for how we did that and the successes that we had there. Then I want to drill down a little bit more and pick up on what Amy's been talking about with a more detailed example of, okay, actually, how do we integrate OpenFast, for example, into a digital twin? So next slide, please, Sarah. So a digital twin is, I guess, a conceptual idea. And if I had to bet, I'd say that every single one of the sort of 60 odd, 47 people on this call now probably have a bit of a different idea, but papers that have been written recently out of the AeroSense project, and I think Sarah's referred to them earlier, are kind of coming out with this idea. Look, you've got a physical system, you've got a software system, and you've got some kind of connection between them. So Yuri Marakovsky is the author, and I'm wishing that I'd put anybody who wants to read the paper can ask me for a reference or for a PDF. But Yuri Marakovsky, one of Sarah's students, has done very nice. Thank you, Sarah. Link in the chat. Has done a really nice classification system.
It's the wrong one, but I'll put the right one in a second.
All right. Okay. Yeah, so that's kind of quite helpful because you can look at a thing and decide what kind of digital twin is, and that's seriously quite useful when you're navigating the swamp of different terms around digital twins and what they actually are. It's nice to be able to say, okay, well, what I'm doing is this. For me, what I say is, okay, if a digital twin is equal to a physical system, a connection system, and a software system, then actually what is that software system? Because obviously, being from OcTube, we're an open source software organization. We build open source tools to help with exactly this kind of thing. So we're all about the software. And for me, when you talk about a software system in digital twins, you've got a set of data services for actually processing information. You've got a set of infrastructure for storing and ingressing and egressing and querying data. And perhaps you've got some kind of user interface on top of that as well. Thanks, Sarah. Yeah, next slide, please. So where we started with the AeroSense project, I think we must have started about 5 years ago now, because the project's long since wrapped up now. We started with this initial concept of, look, you're going to have a sensor node, or actually a node which has a ton of sensors on a blade to measure the pressure distribution. We're going to have a gateway to connect that physical system to the digital system that goes in the cloud. And then on the right of this slide, what I've got is some idea of actually what we want to see. We want to see some measured results of the pressure distribution on a blade. And kind of similarly to how Amy's talking, is we want to be able to then compare them to, for example, simulations, in this case, X-foil. So the end destination, and that is actually a result. So the AeroSense team did a stunning job actually of doing the science to actually work through to reproduce pressure distributions that well. In the middle, you've got some kind of black box, which is kind of a digital twin, and which I've artfully represented with a black box. In there is all of these ingredients of the software system. You need your data infrastructure, your data services, which might comprise sort of scientific applications like X-foil or OpenFast, or maybe more project-specific analyses like turn this data into that data or scrape some external data from somewhere. And of course, you've got a whole bunch of administration stuff, authentication and billing and things like that. So we know that we've got to have this black box. Where do you actually start designing that kind of thing? Well, next slide, Sarah, please. Thanks. Where we started was actually building this data storage decision tree. And this one is a little bit out of date now. It's about sort of 4 or 5 years out of date, but still mostly good. And essentially what we did, for every single kind of data that we thought we'd be getting off of the actual sensors and off of the ancillary systems, so this things like configuration data, SCADA data, and so on, we walked a path through this decision tree and ended up with a conclusion, one of those red boxes. Okay, this type of data needs to belong in a cloud object store. This type of data needs to belong in a data warehouse. This type of data needs to belong in a search index or a relational database or wherever. And so we sat and did that for every single different type of data. Next slide, please, Sarah. And with each different type of data, we're going through that and we're asking these kind of key questions. How much data are you ingressing? What kind of data? Is it sort of raw binary files? Is it occasional event data? Is it like streamed time series data from sensors? And then you've got to think about the middle block. What bits are actually missing from that? What can't we get from the data? Thing is, you need the kind of full operation context. If we're making a digital twin of a wind turbine, especially for doing things like aerodynamics, you need to understand calibration and correction of the sensors. You need to understand the operating position or operating modes. You need to understand things like weather and wind and inflow. And so this very much overlapping with Amy's talk, can we use OpenFast to actually work as a virtual sensor to pull out some of this information at a given time point? Finally, you need to think, okay, what do you actually need to do here? And how do you want to query for your data and show them? By the time you've put all of these things together, next slide, please, Sarah. What we did was essentially we went ahead and implemented that, you know. And what we're seeing here is the end result. So this is an architecture diagram that I actually drew at the end of the project after all of this stuff, which miraculously turned into an almost textbook architecture of a data lake house. So if you were a kind of data lake or data engineer at architect level, what you'd actually do is build something that looks very much like this. And so what I'll do just now is, rather than I'm going to leave absorbing this as an exercise for the reader. Obviously the video and the slides are available online. I certainly don't have time to go through the depths of a data lake, but I want to just drill down for a moment before we finish. Next slide, please, Sarah. Into these kind of two boxes where we have data services running. In this case, so this is how your data storage and your data querying interfaces with what simulations you're running, what analyses you're running. Thanks, Sarah. So the way we did that was we used, and this is admittedly a shameless plug for Octu's open source SDK. So the purpose of this is, and we call it Twined, is to wrap up scientific code as a data service. So we have sort of OpenFast wrappers, TurbSim wrappers, and you can essentially develop any scientific code that you write in Python or whatever can be wrapped up using this SDK, deployed to the cloud as a fully scalable automated data service. And what we do is we publish that online so that it can be actually triggered automatically. So there's this whole protocol of asking and answering questions with a data lake sat under the bottom of it, or a data warehouse that allows you to reconstruct any of those analyses, inputs, logs, monitors, outputs from any single analysis that you want. So you can ask a service a question, you get back an answer, or you can query for that answer at a later date. And at this point, we can run thousands of OpenFast simulations at a time. It's just almost is limitless only on your budget that's available for simulation. So that's how you kind of start tying these things into this wider sort of nebulous concept of a digital twin. I think I'm out of time, so with one last slide, I'll make two conclusions here. I think the first thing is, don't fret about data engineering too much. These massive data lakes, data lake houses, data warehouses, all of the subtleties around data engineering. Actually, the right thing to do is think about your data from both ends. How are you going to ingress it? How are you going to use it? And if you store it in kind of sensible ways, you will actually be fine. A good data warehouse pattern will emerge. Second thing is simulation and analysis codes are sometimes difficult to figure out how to plug into a sort of much more wider automated system and integrate them there. And so shameless plug for the Twined framework that allows you to kind of wrap up your code, turn it into a data service. And it's awesome because there's a data lake and everything, very useful. Bias alert, because of course it's Octu that built it. So thanks very much.
Thank you. Perfect timing. I put a couple of links in the chat while Tom was talking as well we submitted a paper together describing that design process in quite a little bit more detail. And yeah, any questions, please write in the chat. And then I'm going to pass on to the final speaker, Marcus.
Hi,
so go for it.
So I'm going to take over. Yeah, I'm going to talk also a little bit about architecture. And thanks, Tom, for preparing the audience for this topic. I think that will help me in my presentation. Can you go to the next slide, please? So we had, at the beginning of this project, which was called the DigiWind project, we had we formulated a vision of what we want to achieve here. So I've written it down here, but basically what it says is we want something that is open and extendable and also can interoperate with many different components. So kind of what also Tom represented back, I guess we kind of have the same idea of a digital twin. It can be many different things and you want to connect it somehow to the real world. And I think that's an essential component here. So this is also what this picture on the right shows here. So you have a physical asset that is putting something into the digital space, and then you do something with that and hope that you can improve your physical system. That's basically the base what we can maybe agree on when we talk about digital twins, that this is an essential part of it. And when we wanted to develop this, thanks, Sarah, we went through a requirements engineering process. So we looked at use case diagrams and we're looking, okay, who are the stakeholders in operating a digital twin and what might they want to do? And we come up with basically a lot of simulation related stuff. So you, in the end, want to somehow manage your simulation models. You probably have different versions or parameterizations of them. That's from a lot of different tools also maybe. So you want to be tool agnostic and you have to also include some meta information probably about your models in order to use them in the end in your digital twin. In our digital twin, we want to execute simulations. So these are usually dynamic simulations which run over time and show you some transient behavior. And we also want to be able to have a descriptive structure of these things so we can automate them and run multiple simulations with different parameterizations, for example, or connect multiple simulations in one big run in the end. And you need to be able to assemble those simulations. You don't want to define everything by hand all the time. So is there a way of basically automating what you want to do? And then in the end, the most important part was add functionality. So how can you make a framework that can be extended with additional components? And then you have to have a loose coupling between those components so you can kind of construct them in the way you want and then connect them. And this led us to the last point there. We want to have a graphical representation as well to be able to integrate and combine different steps in our process and also run all of these things somehow. And with that, we came to our pyramid design, which is basically the hierarchy of different layers of a digital twin. So I will go through all of these layers in the next slides, but here I just want to say we have developed this pyramid to improve understanding of the digital twin and also show different responsibilities of the different stakeholders and also give kind of an abstraction here. So how can you structure all of this, all of these single components here when in the end you want to achieve something, but you have to run it on some software. What's in between your goal and you're running it on a computer? And then I think we should go into the layers. So the business process model would be on the next slide. It is where your work happens. So this is maybe not even digital yet, but this is where you interact with the system. So you have some goal you want to achieve, and maybe you're a wind farm operator. You want to automate things connected to databases and so on, and you have a specific goal in mind, and this is basically the head of the pyramid. So any process you do here is a single activity that can be later on connected to your digital twin efforts. And here we thought, okay, this is more conceptual layer. So you think about what is your goal and what do you need for it, and then you can think about how to integrate it more seamlessly into your digital twin. And then that gets you into the next layer, which is the process model. And there we found this BPMN language, which stands for Business Process Model and Notation. It's a graphical modeling language where you can define workflows. So it's it's what you can see here on the right. This is a message-based workflow. You can trigger this workflow by sending a message to a server, and then it will trigger other services. So here you can really lay out how your digital twin should work and what services it should run, and then what comes first, what comes next, and you can really build the logic of everything into here. This is what this BPMN model notation language offers to you. So you can have different gateways here. You can connect all the messages that are sent here in a node, or you can bypass them, and you can even trigger human tasks. And this is what I found is an interesting part of it. So you can even integrate the human basically in your workflow. So you have maybe some automated tasks, but then in the end, a human has to review something or has to make an actual decision because the system itself cannot do it yet or something like that. So this really helps laying out what you want to do. And we have an example for one of these services I showed on the other slide. This is the remaining useful lifetime service. We used an example in our paper, which is by the way linked down there in the QR code. If you check it out, I think also somebody posted it already. Thanks. So in this case, we wanted to look at remaining useful lifetime for maintenance planning purposes. So you can investigate here, maybe one component has degraded more than you expect, and then this service would show it to you. In the end, here we use other utility services, and the idea here was an application service can always be built based on other services we have. And here, this is where the modularity comes into place. So we can we have these basic building blocks, and we connect them here together to do something for us. In this example, we run one simulation with multiple models involved, and the models they are only valid for a certain range in time. And then when we go through the past SCADA data to calculate the remaining useful lifetime, at some point we have to change the model, and this is what is represented here with this workflow. So you have basically a simulation template where you put in your models with different versions, and then you get how many simulations you want to run. They are constructed then automatically, and then you run them all in a co-simulation. I think we can go on to the next slide from here. I'm not going to go into detail of all of the core services. These are explained in detail in the paper, but these are always things that can do one specific task, and they should do that task really well. And if you have anything that can communicate via MQTT, because this is our communication layer in between everything, you can integrate the process here. And at the moment, we are wrapping everything in the Docker container. So our simulation runs in a Docker container. The templates used to define simulations are constructed there too. We have our model versioning also being connected via that. And we're also using an ontology here to describe models and simulations, which helps us in the end in the optimization to make it for the computer known to the computer how to connect models and how to replace models when you're working with different versions of them. Next slide, please. And in the end, everything runs on some software, and I also wanted to lay that out here so you can see where all of these things maybe are on your computer. Basically, it's a lot of open source tool we have connected here. I already mentioned Docker, which is a container-based framework to set up all of these microservices. We have ZB, which is the workflow engine that runs these BPMN diagrams and coordinates the messages between all of the single services. And this is an extension we made there with MQTT. And we obviously need a broker, which is Mosquito for that. We have a hosting part for the ontology, which is JNF-Oseki. And currently, we have implemented all microservices in Python, but you can also implement it in any other language as long as you can send messages and get messages with MQTT. And we also have a file server in the system, so you can have a storage for your data or models. And with that, that would be the full explanation of things. So I've shown you today what the process you can set up here to integrate digital twins into your businesses. We have microservices that provide modularity and increase also reusability, so you don't have to reprogram everything yourself. We have ontology supporting all of the data management in the framework, and I've shown the hierarchical structure to separate responsibilities and make clear what belongs into which layer. And with that, I'm done with my presentation. Thank you very much.
Brilliant. Thanks very much. Thanks for the perfect timing for everyone. I think I was the only person who spoke for too long. I think there's a question in the chat. Can you receive a PDF? Yeah, I'm the recording and the PDF will be on the website, and I'll send an email to all the people who signed up. Once it's ready, it'll take a couple of days. Yeah. If anyone's got any more questions for the speakers, please put them in the chat. We're going to move on to this discussion here. If we have some time at the end of the discussion, we can always go back to any questions that are still open. So I wanted to try and run this Mentimeter because we're really, really interested in getting inputs from all of you. There's lots of people here and it's difficult to efficiently get inputs. So we're going to try it with Mentimeter. You can either scan that with your phone, the QR code, or you can use the link which I put in the chat. Or you can actually go to menti.com and put the code 81882545 in. And then, so you should be seeing the first question, which I'm going to present on my screen now. Tell me, if anyone needs the QR code for longer, tell me. Please, otherwise I assume you just got it on the link. So the first question is, do you use or create digital twins? Let's wait a few minutes. We've got 17 people participating and 43 in the call. So we'd really like it if some more people were interested in participating and answering the question. But we can see a trend already anyway. 13 out of 21 do use or create digital twins, and 8 don't yet. So the next question is then, how do you feel about the phrase digital twin? It's a buzzword for what we've been doing for years. It represents what we've been doing, but with an increased level of automation and integration with other systems. It represents a significant advancement in capability over what we've been doing in the past. It represents a completely new paradigm, for example, in the area of computer-aided engineering. So the majority are going for the second one. Nobody's put the first one. So it represents what you've been doing, but with an increased level of automation and integration. Okay. Very interesting. What are you trying to do or achieve with your digital twins? I think you can you should be able to write some sentence or so in there. So you can just put a word or 2 words, just generally, performance, model matching, remote maintenance planning, performance monitoring, virtual sensing, replica of reality, saving resources, predictive maintenance, structural reliability prediction, optimized performance monitoring, predictive maintenance, performance monitoring, control and uncertainty reduction, lifetime extension, predictive maintenance. So we've got quite a bit of maintenance and quite a bit of performance. Some of them are going into decisions, lifetime extension, another performance one. Maybe we should have done a word cloud for that after all. We would have seen the relative one, the relative numbers, accuracy. Okay. And then another question we were interested in is connected to this architecture question. Do you just get some digital twin software, which is ready-made, or do you build them yourself in-house? I realize the question is not quite black and white. You obviously have to use some software at some point, but is it a complete digital twin software, or is it some things that you build together For example, like Tom showed in his presentation. So most of you say in-house. Some of you say specialized digital twin software. So of course, the next question is going to be, which tools do you use for that? So I think Tom's example is his company's tools, or the examples that Marcus gave, the various different tools that he used in his framework. Okay, so Python is one. Any workflow languages or tools or any digital twin frameworks? Find OpenFast, machine learning, Salomonica, Databricks, CMA. Some of these I haven't heard of. 20sim, R, graph databases, RabbitMQ, MATLAB, FMU, Docker. Okay, all really interesting. Time stream database, AWS services, MQTT. Okay, Kubernetes. And then another interesting, and I'll ask maybe some people to give some examples if we have a bit of time, but we're really interested in then what are your obstacles in implementing or using digital twins. So where do you notice that you get stuck, or you don't know how to proceed, or you wish you had some support with open data? Yeah. Budget, clarity of value case, concern about cost, model sharing, IP rights, structural data, no common information models, cost, budget, data set, data quality, linking physics to decisions, scaling up to entire fleet, fine-tuning models, integration of real-time data, diverse collection platforms, access to high-frequency industrial data. So there's definitely one area which is getting data, which in Task 43 is one of the things we're trying to help with. But then there's another thing to do with common information models, model sharing, communication between platforms. And there's another one about budget and funding as well. And then there's another one which is more on the operational level, where we say, okay, how do I link physics to decisions, or how do I fine-tune the models? Clarity of the value case, I think it's always a bit of a difficulty as well. Okay, and then the next question is that going on to this topic of architectures. So first of all, do you think that some sort of common architecture type, property, vocabulary could actually help you build or work more efficiently with your digital twins? The next question is going to be, how do you think they could do this? So the people who are clicking on yes, start to think about how you think they could help you. So literally everyone who's answered so far has said yes. Okay, we've got a bit of a drop off in enthusiastic participants. One says, I don't know. Okay, but building up on that question then, as I said, like if you could have a little think, maybe just give you a little bit more time to think about that as well. Do you have any ideas of how you think these common architectures would actually help you? So you think they would help you? Do you have any either vague or concrete idea about how that would help? Common language to align research. Build it once for industry versus everybody having to pay and build it themselves. Yeah. I mean, both of those things are things that that's what we were in Task 43, we've been thinking along those lines, like why should everyone in every organization start from scratch and spend all their money building some framework or putting nuts and bolts together when they actually want to spend most of the time doing the science? So yeah, a good baseline or starting point to design a DT. Yeah. So I mean, I think something like this framework that Marcus was suggesting seems to be a starting point for something like that. Open source co-simulation platform with possible IP protection. Yeah, I mean that's so you start with a framework and you hope that people use a common framework, but the ultimate version of that would be some sort of co-simulation platform. So whoever wrote that, let's talk about doing that. Shortcut to explain and describe data content, so it doesn't have to be done every time, I guess is the point. Building up on an existing architecture saves time. Yeah, it's hard to build a common framework. Yeah, it's hard to build a common framework. This is definitely true. It's also probably a reason why it hasn't been done. Solution patterns for specific use cases. Yeah, I think that's a good point. I think having one framework for every use case in wind energy is going to be difficult because they're so varied. Democratization of DTs, open source. So that's, I think you're generally saying that would promote these things and help them happen, which would hopefully then improve innovation. So yeah, they're all interesting responses. And then the most interesting question, I really would like to have some answers to this before we stop. Do you have any thoughts about how IEA Wind Task 43 might be able to help? So some of you know Task 43 quite well, some of you don't. That's why I introduced this at the beginning. We're trying to develop industry-wide recommendations, tools, or frameworks for to help the industry as a whole. So based on that, do you think that Task 43 should we be defining this common vocabulary or structure? Should we be providing use cases? Like, are there things that you think that Task 43 could do to help? Getting industry to share data, yeah. Okay, that's good. We're trying. Any ideas about how to do that better? We'd also like to take on. Maybe while you're thinking about the answer to that as well, I'll just open up, like, we've literally got 2 minutes left. If anybody wants to say or ask anything that might be answerable within 1 minute, please take the opportunity to do that now. You put your hand up on the Teams. I'm just going to read what people are saying while I'm waiting for somebody to say something. You're doing it already? Yeah, okay. We're trying. But we would like to focus our efforts on digital twins as well. Align industry work on common frameworks, language with examples. Yeah, strong business cases. Baseline architecture for wind energy can be a good start. Job board. Yeah, I mean, job board is also a topic which we're working on, which has a very high connection with this. Whoever wrote that, I think it's a good point. Website to present what individual people do. Yeah, I saw recently like a landscape, actually NREL had this some landscape diagram in mobility about the different activities, and I think something like that would actually be quite a low-hanging fruit for us to do. So I think that's a good idea. That's what you meant. Common wind farm ontology. Yeah, we're trying to develop a domain ontology. If anybody wants to contribute to that, please get in touch with me. All right, so it's exactly 4 o'clock. I'm going to let you all go. I hope everyone got to ask the questions they wanted to or give the inputs they wanted to. I think we heard some really interesting presentations. We got some great inputs from you, all the audience for these questions. I think we can respond to that now and start to adjust what we're doing. If anyone wants to join, please just get in touch. Task 43, please just get in touch with me. You've got my email, and I will send an email in the next couple of days with the link to the recording and the slides. So yeah, thanks again to the speakers. We'll be talking again soon. Speakers, thanks for doing everything exactly on time as requested. And yeah, have a nice day, everybody. See you soon.
Have a nice day. See you soon.
Thank you. Bye.
Bye-bye.
Bye.
Thank you.
Thank you so much. Bye-bye.
Bye-bye.
Thank you. Bye-bye.